Okay, start. Okay, hello everybody. Enjoying the sun, enjoying the coffee. Not so good actually from the machine, but you know. Okay, we should start. We should start. We should start. We should start. So, here. All right. So, approximately, we are going through my original. Yeah, here. I couldn't hear you because there are so many. Yeah, you may do that. Advantage? No, the issue is what is your model? What are you interested in? Are you interested in finding some kind of uh, particular spectrum data, couplings? Are you on a phenomenological approach to examine direct dark matter detection data? Then you can start directly with couplings with, in my opinion, it's better, couplings with relativistic couplings with protons and neutrons. And then from there pass to nuclei, right? Now, on the other hand, if you have a particular model that you are interested in exploring, and you have an ultraviolet complete mode. Is that correct? Something wrong? See. It's not working?
Is it working? No.
You cannot hear me?
It
The
seems that
mic
it doesn't work.
the microphone is not working. Now yes? Maybe it was not in the right distance from, I don't know. I mean, of course, I cannot hear myself in the microphone. Yes, now there is a return. Yes, now I can hear myself. Yes, that is like a repetition of me. So it depends on what are you interested in, no? If you're interested in testing an ultraviolet complete model, your favorite version of the myriads that there are of supersymmetric models or whatever else, then you have to go that route. There is no other way because your Lagrange, your original theory is coupled to the standard model particles. In the standard model particles, you don't have protons and neutrons. So you start with quarks, you start with whatever other particles there are, elementary particles in the standard model, and then you have to go down in energy, right? And this people did since the 1970s. It's not that it is done only now. I mean, you had to do it from the beginning, and you can see there are many different techniques using QCD. What is the quark content in protons and neutrons, how much the contribution to the mass there is, how much contribution to the spin, and so forth. It's quite complicated, and the issue is that there is no clear control of errors. What people do is to use different approaches and see how different they are. But that is only a measure of the dispersion, so and so. I mean, I don't know. So nobody knows exactly how well they are, unless there are things that are measured. For example, everything that is related to electromagnetism has been measured, and then so you have some data to work with. But then there are other things, other form factors that depend entirely on calculations, and they are better or worse. I don't know. There is a lot of activity of nuclear physicists that actually have come into this field. At the boundary between nuclear physics and QCD, few body issues, few body problems, smaller nuclei and stuff like that. And they are working a lot on that. So maybe we will have, this is fastly moving. Yeah. Did I answer your question? Yes. Oh, great. I have questions. I really like questions. Yes, go ahead.
Usually when you do an EFT, you write the variables compatible with the symmetries, like in this case, Galilean ones, and you put arbitrary coefficients. But actually, these coefficients are related by Lorentz symmetry.
Well, phenomenologically, you can work with both, but I think that we always write Lagrangians with, Lorentz symmetry. And when you're doing that, you are making the approximation of having one mediator, which may or may not be correct. You're still throwing out potential in complete theories. You have interference terms and so on and so forth. Also, you have corrections at loop order, stuff like that. So you're throwing a lot of physics, but at least you are going a little bit above and not considering separate operators, because these operators actually do not correspond, as I showed, one-to-one with an approach with Lorentz invariance. So if you have a mediator, for example, when a mediator, so if the dark matter is coupled, for example, through a magnetic dipole, you have 4 different operators that enter in. So if you consider only one of them or the other, I mean, and the coefficients are depending, nuclear parameters depending. So it could be that actually for some nuclear and nuclei in some range of energies, one is more dominant than the others. The other could be more dominant for some other range, and you are observing exactly the same coupling, magnetic dipole coupling. And if you consider only separate ones, you would think that you're observing different things, and actually you're observing the same thing. So I think that in that respect, at least it captures a little bit more of the nature of couplings, right? Or axial vector, or whatever it is that you are capturing. So, but still it's a phenomenological description. So this may be useful to, if there is ever a signal, right? And you have different nuclei, because you will need different targets, then you can start having a hint of what is the dominant type of interaction. It is a magnetic dipole, or it is a spin independent. They are quite different. And then, of course, you will have to refine and refine. It will be a very interesting problem to have, because at some point you can make contact with other things, like indirect searches and searches at laboratories and accelerators, right? Any other question? So great, because we are going to continue for a little bit with what happens when you have different type of interactions, how they affect this neutrino floor that people don't call floor anymore, they call fog, to give the correct idea that you can get through, because floor is sort of solid, right? It seems to be that actually. So it is a background, it's a irreducible background. If you are very unlucky, then your parameters will be just to give you a degeneracy, and even if you improve your exposure. By the way, I have been using exposure, and somebody after my lecture asked me what exposure is, and I never defined it, because I think, okay, exposure is mass times time. The mass that you use for your detector, not necessarily the whole mass, there is the fiducial mass, right? But in any case, the mass that you used to get your data times the time in which you were taking data, which is only a very small fraction. So MT is, some experiments are kilogram day, some are ton years, the units, right? Different. In any case, so here you see, this was presented already yesterday. In the next generation, as you go down, 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 down here in this sensitivity, you will get to have mostly a background, first a background of boronate neutrinos. In particular, the next generation, XLCD or GAD-MC, multi-ton experiments will have a lot of these neutrinos. And so here you... The current line this comes from 2022. I think it is still correct. This here. SLC? Approximately, right? Yes. Or this is the projection for LC. Not yet. So maybe here, Panda X. You know, they are touching already this background. Of course, this is done for a spin-independent. This plot is done for a spin-independent interaction. This is my major point, right? Spin-independent interaction. So these are the spectrum of neutrinos, at least in a SNOLAB. This is, of course, it changes a little bit. In a SNOLAB, this is what you see. And the boronate is in particular this one that sticks out, and this is the one that actually people are going to be seeing. This is boronate coming from the sun. Then there are, you see here, atmospheric neutrinos. There are some reactor neutrinos contributing to SNOLAB too. You know, neutrinos are from everywhere and everything. But they are subdominant with respect to boronate. So the ones that I'm going to mention, when I mention a spectrum, it will be the spectrum of boronate, because this is the one that we will reach first. Now, if you are extremely unlucky, here it's a bit of a busy plot, but in any case, here there is a black line, which is the boronate. And there is another line that is red. This is SI. These lines are chosen either for a heavy mediator, are solid lines, or for a light mediator, are dashed lines, in such a way that for the different type of interactions that are portrayed here, the mass of the particular WIMP chosen there maximizes the similarity. So we did, this is a paper that I did some time ago, so I know what is portrayed actually. But you see that actually if you're very unlikely, this is about 6 MeV. All of them are between 3 and 7 and so less than 10 MeV. So you get very similar spectrum for this is for elastic scattering and for different type of couplings. Spin-independent, electric dipole, magnetic dipole, and pseudoscalar coupling, so gamma 5. Okay. Now, if you have inelastic in the dark matter only, or elastic reaction in the nucleus doesn't change. But you have this delta, which is the mass prime, the mass of the final dark matter particle minus the initial. And it could be positive or negative. Here you have 10 plus 10 keV minus 10 keV. And here is, I cannot see, minus 50 keV. And the spectra are not as similar. Actually, they look quite different here. But the spectra, the degeneracy of the spectra is not the only thing that is there. The issue is that this background is at low energies. So when your spectrum of dark matter favors, namely you have a majority of your rate, the majority of your rate at low energies, then this particular background hurts you in your discovery reach, which is what I will show in a moment. Now, I have mentioned several different type of interactions, and I'm classifying them because of differential cross sections. And if you find that, as I do, I'm sort of old school, doing everything with computers linking programs, right, is a bit too transparent, and you would like to have an idea of the cross sections. We made here a compilation writing down the cross sections, at least for one mediator, so you can really see the dependence on Q, the dependence on V, and so forth. So we made a compilation of all of these differential cross sections, and you have different types. A spin independent and a spin dependent with heavy mediator has no dependence on Q. Q is the momentum transfer. There are some that depend Q to a power, a positive power, 2, 4, or 6. And so the spectrum is large at large energies, and so they are less affected by low energy backgrounds. That means that this spectra goes to zero when the energy goes to zero. And they peaks someplace and then returns back. Okay? The maximum is far away from low energies. This is a magnetic dipole, electric dipole, a pseudoscalar, scalar, pseudoscalar, and so on and so forth for heavy mediators. This is HM, is heavy mediators. This is the type of interaction. This is anapole.
No, but heavy mediators are dominated by the Q0.
Sorry?
I would say that the heavy mediators, the signal of heavy mediators is dominated by the Q to the 0.
Exactly. No, it's dominated by Q to the 0 in a spin independent. Otherwise, not. That's why I'm saying M, magnetic dipole, electric dipole, pseudoscalar, scalar, pseudoscalar, and anapole. And I can show you all of them if you want in my paper, not in my, yes.
Another thought. So let's assume just spin independent normal cross section. The neutrinos, the cross section scales with number of neutrons squared. Now that's not the case for wings, right?
Well, it could be. It could be actually.
It could be, but I'm just thinking in xenon we have all these different isotopes. So could we take advantage of that? Right, 124, 126, and up to 136.
Yeah,
With different number of neutrons and protons.
in principle, yeah.
See, yes, even for a spin independent, you could have a very refined. Here we did something a little different, which was to consider. Not, but it's true. If you consider Fn, the couplings could be isospin violating, right? And or isospin conserving, and your answer will depend on that. For sure, you can do that. This is an even bigger difference. Here is an even bigger difference because you are coupling to different properties, not the number of neutrons or the number of protons, but you are coupling to different properties. Now, if you are these light mediators, right, and in this type of interactions, MC is millicharge. Millicharge is through a dark photon, for example, right? Millicharge. Here there is no spectral degeneracy, but yes, it is enhanced at low energy and you are killed by it. So actually, this is what we did. We considered, and I'm not going to show you, we tried to do something sort of realistic for the future, and we did it for different type of materials. I'm going to show you essentially only for xenon, right? But So here it is, assume that, and we did the analysis of the rich without neutrinos and with neutrinos. Without neutrinos is the black line. This would be your rich for 0.1, this for 1, this for 10, and this for 100 kiloton years. That's your exposure. And then in the same line type, dotted little trays, little bigger trays, and then solid. Same thing, same order. The red one is with the neutrino background. Now you can see very well that if you are here, if you are sitting, and this is for a spin-independent heavy mediator, if you are sitting there, oh wow, you can increase, 4 orders of magnitude your exposure, and you will practically not move from there. But if you are anywhere else, you will gain, but you pay a price. So you see that instead, this line, for example, the red line here, that corresponds to 100 kiloton years, is at this level instead of being at there. However, if you have, here is what, magnetic dipole, heavy mediator, then you see actually that this degeneracy is not that much. You improve a little bit. And here, if you go to heavy enough particles that would require actually to go to high energies, I think that we had a window here between 50 and 300 kVs, because actually the spectrum goes up and goes down again, so the maximum is at high energies. Then you're not bothered, practically. And, yeah. ¿Cómo? What did I say? I made a mistake. This is the exposure, no, but kiloton is too much. 100 kiloton. Thank you. Even now that I read it, I didn't. No. Thank you for telling me. I will correct that, because otherwise 100 kiloton years will be really amazing. But okay, no. This was 0.1. So you see, 0.1 is already superseded by some limits. I mean, this is small. 0.1, 1, 10, and 100 ton years. Okay, so the same thing here. So this is now, I show you 2 of them, but without going into all the detail, you see that for some interactions, you have the same thing that I showed you before, that if you go to large enough mass, about 50, I would say about 50 GeV, then you actually are not that bothered. In some of them, you are. These are for heavy mediators. For light mediators, you are in the other end of this. You are disfavored. You are really disfavored, and so actually you do improve, but the cost is quite a bit of this background. Okay, so I wanted just to show you. And this is for inelastic scattering. For inelastic scattering, again, still you lose some. In any case, you see the type of games that one will have to play if there is a signal, because of course, if there is no signal, you don't know exactly. But if there is a signal, then all of this will have to be used in order to interpret them, to give the best interpretation for the signal. Okay. No. Light mediator and heavy mediator, I use it many times, means that you use a contact interaction, or you use 1/q squared for the mediator, for the propagator. It means that. Namely, either you consider it much heavier than your momentum transfer or much lighter than your momentum. So technically it means you just change the propagator, 1 over m squared, where m is the mass of the mediator, or 1 over q squared. Yeah? In the middle, it's more complicated, and we didn't do it. In the middle, of course, it could be, because then there is a transition, right? But it will be, for this kind of analysis, it's not worth considering. It will be 200, precisely 200 or about 100, 200 MeVs for a mediator. It will be a special case. You have to do it. It transitions between one to the other. Yes? Okay.
Whenever we have a light mediator, can we say that we have a UV complete theory?
No. It's phenomenological. Even if it is light or it is heavy, this is a phenomenological choice. Having a complete theory means to write a Lagrangian with quarks and gluons and whatever all the other interactions are that you have. And from there on, you go down. And then the mediator has the mass that it has, and then you compute. But otherwise, at this stage, it's a phenomenological choice. Okay. So if you say, well, are there models actually? Yes, there are many models that go below the neutrino fog. And this is actually this plot. I did this plot in this. Were 3 people working on that. So here you will see, if you can see anything, some of the models that I mentioned before. For example, elders are here. This is elders. This is SIMP and an elder. I mentioned them. This is a particular Majorana candidate. And then in the others, sincerely, it's too small. I cannot see. Triple Majorana and NMSSM and things like that. In any case, if you go to this paper, there are references to all of these models and the predictions for this. And moreover, from the point of view of dark matter, here you see the classification that I have been sort of using. This is another way of presenting exactly the same. So here you can order many models, and there are many of different type of, either to be in the visible sector or in the dark sector. And to be highly predictive or practically non-predictive at all. So in this visible sector and highly predictive, you have, for example, phenomenological MSSM, non-minimal MSSM, and so on and so forth. Multiple Higgs models, multiple Higgs doubled models, and so on. These are complete models, but they could be complete models in the dark sector too. There are complete models in the dark sector that rely only on a portal to communicate. Then in the level of predictiveness, there are intermediate models in which you consider simplified models, in which you have one mediator. For example, the one that I was mentioning, I would consider is a very simplified model. It enters into these categories. And then a single effective coupling is below. In some of these models, you make sure that your dark matter has the right relic abundance. But of course, it has the right relic abundance. You have as you know, most of the dark matter particles are produced. Their density and spectrum and momentum spectrum are produced before BBN. And we don't know the history of the universe before the universe, before the temperature of the universe was something like 5 MeV. 5 MeV and up to now we can follow. Before we don't know. And so, people attempt, but there are many variations even in that. Okay, So now I'm going to stop talking about cross-sections. We devoted a lot of time about cross-section. And let us talk about the halo model. So we are going, so this responds to the question, how many dark matter particles are passing through the detector and with which velocity distribution? This is very important. If you don't have particles in your detector, you are going to detect nothing. There was this comment the other day, and I will repeat again. I think they did an estimate, right? I may be wrong by 1 order of magnitude or something. If you take the size of the solar system, I took 30 astronomical units. I pass it to parsecs, took the cube of it, and I multiply this by about 0.4 GeV per centimeter cube. 0.4 GeV per centimeter cube is about 10 to the minus 2 solar masses per parsec cube. You multiply these two and you get 10 to the minus 10 to the minus 13 solar masses. You can do that actually, and then you tell me exactly how, because I may have done something wrong. And 10 to the minus 13, 10 to the minus 14 solar masses is in the range of the asteroid mass range, in which you can have the whole of the dark matter made up of primordial black holes, for example. So if that is so, if you have primordial black holes, 10 to the minus 14, 10 to the minus 13 solar masses, you will have one in the whole solar system volume. And still, all your measurements at large scale, all your astronomical measurements, and also your simulations would be fine, because these are perfectly fine dark matter candidates. That's the question I think you ask about. Okay. Now, if it is particles, it will never be so. If it is actually particles, it will be very difficult to have this aggregation of particles, right? So there will be a diffuse component. Even when you have the axions tend to form mini halos and so on. Only a part is in the mini halos. The rest is diffused. So, for particles, I think it will be a large part of it will be diffused. It may not be the whole 0.4 per centimeter cube, but it will be a fraction of it. Yeah. So it depends. But, in terms of, the question was, what is that one is measuring actually in terms of the solar system? The only way of detecting what is going on in the solar system is if we have direct detection in the laboratory. That's why this is so important, actually. And I will, if I get to talk about this, because I'm very talkative, I will to say that actually we could infer the properties of the halo, actually, using direct detection data. All right, this is a halo-dependent versus halo-independent data analysis. All right. In any case, the halo model, the standard halo model, actually, is a good first approximation, although one doesn't expect to be exactly correct. And it implies an annual modulation of the rate. So let me talk about the annual modulation. The annual modulation of the rate. So you change from the velocity of the Earth around this is what this plot showed. The plane of the motion of the sun around the galaxy. So the velocity of the sun, prevalent velocity of the sun, it has a little variation, is at 60 degrees of the plane of the ecliptic. So you see that actually these two vectors are not by all means in the same plane. They differ by 60 degrees. And so only if you say that this is a little variation, a little perturbation with respect to the velocity of the sun. So mostly the velocity of Earth with respect to the galaxy is due to the velocity of the sun with respect to the galaxy, and it changes a little bit. Our velocity would be maximum at the beginning of June and minimum 6 months later. And so this is, then you compute the usual rate, when you have only a spin-dependent or spin-independent interaction heavy mediators, you have this differential cross-section goes as 1 over the speed square. And then the 1 over the speed square, you cancel one of these powers with the speed that comes in the flux of these particles, and then you have this integral. This is the integral that appears, that codifies the whole, the contribution to the rate of the velocity distribution. This is an integration in D3V, but if there is no directionality, if you are averaging, that's what we do, we are averaging with respect to directions, then you can put it as function directly of the speed. The speed, this is the speed distribution. So the maximum changes from June 1st to December 1st at about V min of 200. If you see, this is the solid line, is the speed distribution. You see, this is a Gaussian in velocity, in speed. This is the Gaussian. So this is in June 1st. Is the solid one. And then 6 months later, December 1st, this was done with parameters in which the maximum and minimum were in the June 1st and December 1st. They change a little bit with the parameters you choose. But you can see here then that at December 1st, at low velocities, the distribution is higher in December 1st, and above a certain energy, a certain velocity, which is 200 kilometers per second, the opposite is true. And so this is eta. You see that it changes actually which one is higher. And so the annual modulation is due only to the velocity of the Earth, so you can make a Taylor expansion with respect to a small perturbation, which is the velocity of the Earth. And you can see that the amplitude of the annual modulation is linearly dependent on the velocity of the Earth. Since the velocity of the Earth is 2930 kilometers per second, and the velocity of the sun around the galaxy is 300 kilometers per second, then you have a 10% effect. So you can expect that at most your annual modulation amplitude would be 10%. Now, the annual modulation amplitude leads to also a, well, you can make an harmonic expansion, and the first would be the one that is in a year period is then the annual modulation of the rate. And you can see actually that the modulation amplitude changes sign, precisely because of this difference that I mentioned before, what is dominant in which. So at the small enough energies, what the small energy means the recoil energy that corresponds to the V min, that is 200 kilometers per second. At that point, it changes sign. There are effects that you will have to take into account really if you, at some point, you have a signal. And one is that the sun, there is a gravitational lensing by the sun.
Sorry, Graciela, what changes sign? Sorry, I didn't understand what you said.
It changes sign because this is the rate in June minus the rate in December. And what is which one is bigger depends on the recoil energy, which depends on the V min. So at low recoil energies, you have that December is bigger than June. So if you define it,
You're assuming something on the
no, I'm assuming nothing on the cross section. This depends only on the halo. This depends on the halo. This would be true for any cross section. The only thing is what is your V mean, where you get to see this. If you're observing.
So for me, you can factorize the halo part
This is the halo part factorial.
only if you assume that the cross section is a constant.
Oh, I'm doing this, as I mentioned, for SI, for SI or SD. When you have, this is the only contribution. For SI or SD, heavy mediator, then you have 1 over V square. The 1 over V square you cancel with the V that appears in the flux, and then you have 1 over V. Yeah, right. If you have something more complex, I repeated twice practically the same. But you know what? This is good because I also miss things. Everybody does. So the students will not feel bad because of they miss things, because everybody misses things. And you say, what happened? What happened? Okay, so doesn't matter. Any mediator? Well, no. For any mediator, and that's the point that I'm going to do in a moment, because this is only if you have your eta function. So if your halo has only one function. This is what I was going to. But before I move, before I will address your issue, even if you would have only the eta function, with whatever you want, you have the effect of gravitational lensing of the sun, which depends again on the velocity of the particles, right? It doesn't depend on the mass, it depends on the velocity. Okay, the gravity acceleration is the same for any mass, right? So a photon is accelerated as much as a pebble, but the pebble falls because the initial velocity is very small. The photon is moving very fast and therefore is not affected. The acceleration is the same, but it doesn't change it. Well, this is exactly the same. It's an issue of velocity. So dark matter particles that are at a small velocity are affected by the sun. They are collimated as they pass. So this is the direction. So we are here. There is the wind. Let me put myself in the rest frame of the sun and seeing on average the particles coming through. Okay. So if the Earth is here, you don't see any effect because the sun is on the other side. But when you see here, the effect would be maximum in this collimation. But only you see it's about a few percent. It's a few percent, but your annual modulation is also a few percent. So actually, these people, Lisanti, Lee, Peter, and Safdie, here in 2013, computed, made these calculations. The numbers they use are a little bit outdated, but it doesn't matter. The effect is still there. And what they found is that for velocities that are smaller than 200 kilometers per second, V mean, in order to reach this V mean, that means that for whatever, there is a combination. You will have to be possibly in very low threshold in order to do that, but depends on the combination. But in any case, if your V mean is below 200 kilometers per second, the maximum of eta shifts by 21 days, right? So this is an effect that at some point you will have to take into account if there is an annual modulation. I'm showing you all the complications just to have an idea of all the things that will have to be taken into account, comparing. This is what he was mentioning, right? Imagine that you have now a complicated interaction. I'm always using this magnetic dipole because I chose magnetic dipole. It doesn't matter. I'm using always that as an example. And here you have some, you see that here I put the 1 over v squared outside, and this multiplies this term and multiplies that term. But this term is velocity independent, right? So that means that I have two functions now when I integrate. One is this eta function, and the other is the integration. I don't have the 1 over v squared, so this is the v, the speed, that comes in the flux, that is in the numerator. Are you with me? Yes? Are you with me or not? Yes? Okay, so you have two. And the coefficients are nucleus dependent, target dependent. That means that if you have this interaction and you're observing the annual modulation in two different, with two different detectors, assume fluor and xenon, whatever, you will see vastly different annual modulations. The annual modulation, here we included gravitational focusing by the sun. This is with gravitational focusing, this will be without gravitational focusing. This is how they change. But they change differently. This is, I mean, I'm not going to go into all the details. They change differently. And what happens is that here it is the time of maximum, for example. You see that the time of maximum will change depending on this is the time of maximum. It will change with your target, and even the shape of the modulation. For example, in xenon, the modulation is better described by sinusoidal time dependence, cosine or whatever sign, and fluor is not so much; it's much more deformed because of the interplay, okay? Without entering into the details, it can be that the annual modulation is not seeing your mass maximum and minimum. It will be seen as a maximum and a minimum and some deformation and so on and so forth that is actually nucleus dependent. And it would be fantastic if you would get that, because then you would get the handle on the type of interaction that you have, okay? All right. Now, let me talk about deviations from the standard halo model. These things here, triaxiality, these were the debris flows. This is potentially a stream. This is a dark disk. These were about 10 years ago. This is the world before Gaia. And then there is now the world after Gaia. So this is the before and after Gaia era. Now, Gaia finished was decommissioned, as people say. I wonder if you know what happens to the satellite when it's decommissioned. What do you do with a satellite that is decommissioned? No. It will be very dangerous, actually. If everything that goes flying around you throw on Earth, it will be... No, either you throw it in the sun or you put it in orbit. In this case, it's in orbit in the sun because from time to time they're going to wake it up and get some data. Yeah, but in any case, so far there have been 3 data releases, and there will be a few more. I don't know how many more because the data taking hasn't been processed yet. And this has changed enormously many things. So you see paper after paper after paper. This thing is evolving. So I will show you a few results. It doesn't mean that in a year there will be more, in 2 years there will be more, and so on, until all of this data are absorbed in the community and people that are doing similar work actually figure out what is the best way of doing things and so on. So this is in particular a result of the best type of simulations. These are hydrodynamical simulations, illustris and so on. Of almost 100 Milky Way, should be way with uppercase, Milky Way analog simulations. And they use some of the data, the Gaia data, in order to corralled or choose or actually change somehow this data so that they are better adjusted to the Milky Way. Gaia has found that a big portion of the stars around the solar system come from a merger. They have radial velocities that are much larger than the usual halo ones, and they come from a particular merger with a sizable galaxy, about 8 to 10 10 to the 9 years, 8 to 10 billion years ago. This feature is called Gaia Enceladus. And Gaia was a goddess, right? A Greek goddess of Earth. Enceladus was a giant son of this goddess. So this Gaia Enceladus is like a feature. They call it also the sausage, but you only see the sausage if you are in the particular a space, which is a velocity space. In velocity space, in different components, the velocity looks like a sausage. So they call it the sausage, the Gaia sausage, or the Gaia sausage Enceladus, or whatever you. Okay. In any case, this is this contribution. And then they did several things. They reconstruct. This is the full reconstruction, and the dark line here is the standard halo model, actually. And they say that like, it's not that bad. The standard halo model is not that bad. It reproduces pretty well. However, this analysis does not resolve local structures. One, because the speed distribution is taken in an azimuthal average of around the simulation, right? So they take the curves to be indicative, making an average over an annulus. And so you lose any local features that there could be. Also, the simulations have I cannot read well, so almost 300 parsecs of softening length. That means you cannot see whatever it is inside 300 parsecs. An additional, they didn't take into account the gravitational effect from the sun either, any gravitational effect from the sun. So this is a sort of a smooth component. But Gaia has seen, unfortunately, you know what? This looks much better in my computer. So if you have the occasion, look it in the computer, because sincerely, it's quite bad. You cannot see anything here. This, better, yes. This is better, yes, okay. So this is the same disk that is there. You can see this is Sagittarius. Remember the first day I showed you the Sagittarius? Sagittarius is a dwarf galaxy that has gone around the galaxy several times. It is being tidally disrupted. And when something is tidally disrupted, there are two trails. One that is before, and the other is advanced and delayed trails. Here it is, one of the trails. This is another trail, but there are several. And look, these are all different streams, of course, observed in stars. And there is an uncertainty in how much dark matter is in each of these streams. A large uncertainty, actually. So this is what is called the leading trail and the trailing trail. The leading trail, you see, goes not very far, but these are the stars, right? Go not very far from the sun. So if there will be a thick stream of dark matter, the dark matter from the leading trail of the Sagittarius dwarf galaxy, Sagittarius leading trail, would actually be seen as a stream in dark matter on Earth. Okay, and this is what the people have assumed, some properties, okay, some properties, and then you would see a spike in some particular direction. If you don't have a directionality, you will see a spike at some particular velocity, and you will see a feature, therefore, in your eta function or whatever function you need to use. So this could be one. Now, using all of these streams, or many of them, this is a recent, it's about a year ago. Gelmini, Amina Gelmini, and I don't know this person, they have made an analysis of how triaxial the dark halo can be in the location of the solar system. And they find that it is very mild. This is their result. So on this side, this is Q. This is a parameter that indicates how oblate is here, or prolate. Oblate is like this, and prolate is like that. I always make a mistake between oblate and prolate. So that's why I put the picture there. So oblate would be here. So there have been many different measurements, starting in 2010 and so on and so forth, going now, this is their result. You see that their result is almost spherical. In the location of Earth, actually, this is within in the inner 20 kiloparsecs. It's not really understood if the oblation or prolation is the same all along, or it changes with the radius. It could be that the outer radius is prolate and the inner radius, the inner part, the outer part and the inner part is oblate and the other is prolate. But in any case, at the location of the solar system is practically spherically symmetric. So there is no triaxiality, at least not in the bulk. Something else that is very important is the Large Magellanic Cloud that I also show you. It is one of the two Magellanic Clouds are those satellite galaxies that you can observe by eye. This is a galaxy that is entering into the Milky Way for the first time. It didn't go around ever. It's just incoming with all its dark matter. And so it's incoming at some large velocity, and it brings showers towards the solar system, high velocity dark matter particles that are their own, and also accelerates some that are from the Milky Way. So it produces, so here the black line here is without, and the blue line is the velocity distribution with the Large Magellanic Cloud. And this is the eta function. You see that it produces an overdensity at very large. It produces an enhancement of the distribution at large velocities. A dark disk, and this would be a very prominent dark disk. So I just show you that the LMC changes this tail, the high velocity tail. What about, a dark disk would actually enhance the lower end, but this is really quite pronounced. And this would, you remember dissipative dark matter? That part of the dark matter could be dissipative, and if it was, then it would end up. If it was a double disk dark matter, dissipative enough to actually fall into a disk, then disks will be pervasive. And they said that it could be up to 5% of the local dark matter could be in that component. There have been a revision using, again, Gaia data, and they find actually, but this is the result So this is the result 2017. They conclude that the dissipative dark matter can account for 1%. So maybe it is not as prominent. Shards. Shards are pieces, right? There are a lot of shards found by Gaia. But of course, the dark component, the dark matter component of all these structures, destroyed structures, is unknown. And so here there is a modeling, some kind of modeling. First of all, there is a model that is called SHM++. This was done by Evans, O'Hare, McCabe in 2018. That includes the distribution of Enceladus. Gaia Enceladus. So this is the Gaia Enceladus. It's a subdominant component. So it would be the, this is the SHM, the Maxwellian distribution that we have seen. But the piece is in this type of component. And they call it this SHM++. And then they added other shards. These are velocities in the frame of the sun in different directions. So you will see in different directions, you see different structures in velocity. And then in a speed at the position of the solar system, you see something like this. So there will be the SH++ line, and then some other spikes here and there. So this is what, and the effect of how much the effect is depends crucially on the density function in these shards. Here it is assumed that it's 10%, but it's rather arbitrary. Okay, given all these uncertainties, oh my God, I have half an hour. Okay. In any case, it doesn't matter. Should we actually try to elucidate, instead of assuming a halo model, should we try to find out, if we ever have a signal, what the actual halo is? And this is the idea behind a halo-independent analysis. And the two are complementary. So what you would do is to assume a halo model, regular, whatever, something reasonable, let us say. Then you get some type of interaction, some type of mass. Then you put this mass and interaction, and you do not assume anything about the halo, and you try to reconstruct the properties of the halo, namely this eta function, for example, or two eta functions, or the velocity distribution itself from the data. That's the idea. So, I will mention only briefly what it is. So let us start again with recall what is the event rate. So the event rate, we said that depends on the halo in this way. This is the number density, the density divided by the mass. You see the flux, this is V. The cross-section, the sigma AdT, and you're integrating, given a velocity ER, you're integrating above a certain V min, which is the minimum velocity that will give you on a target T, will give you ER. Notice that the relation between V min and ER depends on the target, on the mass of the target. So if you start from an ER, then you have one value of V min for each target nucleid in your detector. Usually in your detector, even if you have only one element, for example, xenon, you have several isotopes, right? Or some detectors have more than one element even, and then they have also their isotopes. Isotopes and elements I'm calling nuclides. Okay, for each nuclide, there is a relation between ER and V min. Okay, perfect. So the density and this distribution is the only thing that characterizes the halo and should be common to all detectors and all detections, because the halo is unique. You are in the same halo. Now, if the velocity, if the differential cross-section goes as 1 over v, then you have this function, this famous function, eta. And eta of v mean, this is a function, is a function of v mean, it's a function of the lower limit of integration. And that I said here, that if you are summing over different target nuclides in your detector, then v mean is a function of t. You see that there is no one v mean for a detector that corresponds to an ER. It's not unique because you pass through the mass, okay? Now, if you give this function, in this case, then the only thing that remains after you have decided what is your interaction, in both cases you have to assume an interaction, but the particle model. And then in this total cross-section, you extract a particular constant that you call your reference cross-section. Sometimes it is chosen to be the cross-section with a proton, but it's not necessary. Any constant would do. You define it well. And then you get these plots for exclusion plots or for regions of interest in the mass and sigma ref plane. Okay. Now, assume that I give the mass. I give, again, the interaction. I have to always say the interaction. Then I can actually derive this function. This is the purpose of halo independent. So, and this function is common to all detectors. And that's the point that will allow you, in last instance, also to determine what is correct and what is not, because you will have, like always, you need many different targets. Okay, so now, as I said, ER and V mean cannot be independent variables. Either V mean is a function of ER given a target mass, or ER is a function, but you cannot have both as independent variables. On the other hand, ER is not directly observable. It's not observable. What you observe is some proxy for it. You have seen actually that the only thing that the detectors detect is either phonons, that if they bounce around enough, they heat up, so it's heat. Some charged position, electrons, charged position, and some light. If you have luminosity, okay, light. So that's what you have: light, charged position, or heat. And with that, you have to reconstruct your ER. But what you are measuring is, I call here E prime. E prime could be some number of photons produced by photomultipliers, or some ionization, whatever, right? E prime. And then you have here, they are related by a probability distribution. This is the probability that, having observed E prime, you actually had a recoil, which is ER. This is a probability. This is the energy resolution function. So at the beginning, the earlier versions of halo-independent method used just the relation with the ER additive with one only target nucleus, namely a unique relation between ER and V mean and SI interactions. If you assume that there is here only one, instead of summing, you assume that there is only one target, then this is simple, because then the relation between your rate and eta is just algebraic. It's an algebraic relation. And some people still describe in this way. They don't sum here. They say, well, it's the same. To use ER, it's the same as V mean, and then you can pass from one to the other. That's it. Life is not so simple. is actually a convolution. So what we did, starting in, this was my work with Paolo Gondolo in 2012, and then I have worked on this repeatedly, doing different things. What we did was to choose Vmin as independent variable. Then we changed the order of integration. So when you have here an order of integration, right? You see that you have here an integration in velocity. You have an integration in velocity. You have an integration over ER. Well, let me exchange the order of integration. If I exchange the order of integration, I can put the differential rate, observable differential rate, either differential or integrated, as the integral of a kernel that depends on the particle model and the detector, and a function that depends only on the halo model. And so the problem now is having many data points that may consist of single events at particular E prime energies, or if you integrate over bins, binned data, yeah, so several numbers of bins, I have to reconstruct a function. Now, this kernel acts like in cosmology they call it window functions. It's a window through which you can peer through to this function. When this function is zero, and this function is zero for low enough and large enough velocities, it depends on the resolution of your detector. These functions are non-zero only in a certain range of Vmin. Through that Vmin, your detector can illuminate, can tell you what is eta in that range of Vmin. So different detectors illuminate, point to different regions in Vmin. Again, you will need several different detectors to do that. The problem is the following: how to determine a function. There are many methods to parameter estimation. For parameter estimation, there are many likelihood methods, etc. But in this case, you need to extract a function. Okay, we have done some progress in doing that. And so we have done several analyses. I'm not going to enter into all these details, but in any case, we started by finding, for example, when there was at some point about 10 years ago, more, yeah, 10 years ago, there was an experiment, CDMS silicon, that had 3 events, for example, and we analyzed these 3 events. There were several detectors that had maybe a hint of light WIMPs in their detectors. This is just as an example. And then we found the best fit. Now, this is difficult to see, but the best fit for eta is this very weird piecewise constant function. Here it is, piecewise drops down, piecewise drops down. For three pieces of information, you cannot obtain that much. It's only 3 events. What can you do? It's not that you get a very good description. But the issue is that we always found these eta functions that were piecewise constant. And the issue is, why piecewise constant? We could prove it for a particular likelihoods and not for others. It was driving us crazy. I mean, my collaborators and myself, until we understood the following. And it took a while because we had to use convex geometry. Using theorems of convex geometry, if anybody is interested, I can explain about 10-15 minutes the nudge of it, the main point of why this tells you, this way of writing things, these theorems, very general theorems. One is the fundamental theorem of this convex geometry. It's called Kara-Theodori theorem. And then some other corollaries and so. I assure you that without having to solve this problem, I would have never learned convex geometry. It's out of desperation that you end up with this kind of theorems, because actually we could prove that the best you can do when you have data points, some number of data points, assume d data points. That could be d different measured events, or it could be d event means. Okay, whatever it is, d data points. Then the maximum that you can do for f of v, and this is done assuming isotropy, so you are not measuring average, there is no directionality, and therefore f of v, the speed distribution is enough. The speed distribution needs to be written in this way. This is the best you can do. It's a sum of delta functions with some coefficients here, and the number of terms here is never larger than d. You have at most d. Usually when you make your fits, you find that's much less than d. So now, if you put this as your halo model, now you have transformed your problem of finding a function with the best you can do, which is actually to find this at most 2D parameters. And we have transformed that, and this is a general theorem. This is the best you can do. And for us, this was a breakthrough because, of course, now when you integrate, the delta functions, of course, you get the piecewise constant pieces. You get all theta functions, right? So in any case, there is a lot of work to do. And moreover, now we are doing something, and I'm going to mention because I'm really, there is an exactly equivalent problem, which is to determine the spectrum of reactor neutrinos through sevens, namely through coherent elastic neutrino, whatever, neutron scattering. Okay, neutron scattering, where they call it sevens because instead of the nu you write a v. So coherent electrons is CF7. Okay, coherent elastic. You require a very low threshold in order to do that. Reactor neutrinos has the spectrum has not been measured below the threshold for inverse beta decay. So at very low energies, there are only calculations, but nobody has been able to measure because you use inverse beta decay. So there is this idea of using a detector, and this is exactly instead is formally the same. Instead of having your velocity distribution of dark matter particles, what you have is your spectrum of neutrinos, and we are doing that now with fake data and so on, and that helps I think develop show how this how good this method could be in comparison with others, because sincerely inverting these convolutions to get a function in the convolution is not an easy problem, and there are various techniques that involve inverting matrices that are huge matrices. Inverting matrices is awful. It generates a lot of oscillations in your parameters. So in any case, we are comparing this with other methods. Okay, this is for something completely equivalent and different. In any case, there is lots of work to do in this method. Okay, how long? Yeah. Okay, I will finish next time, but in any case, I would like to mention, because my last, you know that today was a little bit here, a little bit there, a little bit there. The last little bit is directional detection. And there are different ideas for directional detection. There is a statistical directional detection, but that is not what I'm going to talk about. The statistically, right, you can have some kind of anisotropy, some directionality information. For example, in xenon, I'm not sure that it has been done. I have seen some ideas in argon. Because you have a drifting potential, you have an electric field, right? To collect your charges. I'm sorry, Laura. That's my theorist view of what you do. But in any case, you have a field, right, in one direction, which is to collect your charges. And that introduces some degree of directionality. So if you have very large numbers, maybe you have some idea of directionality. But that's not what I mean. What I mean are these efforts to actually measure single event momentum. Not the energy only, but the momentum. So they see a track, they see the directionality of the recoils. Now there are several here. They are prototypes mostly. They are maybe 1 meter cube at most. Now there are several. In the future, they have joined forces to become one collaboration with many different detectors. I don't know where it will go, sincerely, but it has. You cannot very well read. Maybe here better actually. Yeah. So they have a whole program, and they have many prototypes all over the world, in Italy, in the UK, in Australia, in Japan, in the US. And these two are in the different places in the US. They are sort of small. They are a TPC type of detectors. So I'm not going to tell you that the experimental part. I can't, but I can tell you how the rate is computed, and that was. But I'm not sure if I should continue. Hey, I have 5 minutes, so I will continue. At some point, we interrupt. So I'll tell you how the rate is computed, which is different, right? It's different. First of all, what can you do with it? A few dozen events would be enough to detect the dipole feature, namely where most of the dark matter comes from. And it's called Cygnus because it comes from the direction of Cygnus. This is where minus the velocity of the sun is coming from. So the wind will be mostly in this direction of Cygnus. So here you can, these are Molveide. I never know, is it correctly pronounced, Molveide? I'm not sure. I'm Molveide, maybe? Molveide. Anybody knows exactly? Because it's German, yes. Molveide. Okay, it's German. Yes, Molveide. I always say Molveide, but this is my Spanish accent. Don't believe me. So believe her. Molveide, right? Okay. So this is an example, but really a few dozen events. It's not much that is required. So even if these are gaseous detectors and so on, a few would be enough. Moreover, you will see after this you need more than a few. If you have more than a few, maybe 5 times that, you will start seeing a daily modulation of the signal. That will depend on where on Earth the detector is. But you will see it changing. Actually, this direction will be changing once per day in the sky. This is how you compute the rate, and maybe I will go very fast here. You need to keep you need to keep the direction now. So there is a double differential in the event rate per unit detector mass, right? As always, as function of both the recoil energy and the direction. So you need to keep this. The omega is an infinitesimal solid angle around the recoil direction. The azimuthal, there is an azimuthal symmetry of the scattering around the WIMP arrival direction. Each WIMP comes with a certain MV, and then there is a scattering that can happen actually around that arrival direction. Then you go, if you see here, what is cosine theta? I don't know if you remember, but this gives you the definition. If you take out the cosine theta, this would be the definition of V min. So actually, the V min square, this would be V min square. So actually, the cosine of theta is V min, sorry, here V min is V sub m, it's V min, is divided by the speed V. So impose these relations through a Dirac delta. This is the same, V cosine theta is the same as V dot, the direction of Q. Q hat is the direction of the recoil. And then you replace this. And remember that the energy differential cross-section for standard contact interactions is this. This is only for contact interactions, for spinning the, I mean, all of this would have to change if you have a different differential cross-section. But this is done for the usual spin-independent heavy mediator, all right? And so this is the equation that you have. And this is a very interesting function. You see that actually it has become a function of V min and the directionality of Q. This function, this is the three-dimensional radon transform of the velocity distribution. This was done by my longtime collaborator, Paolo Gondolo. This was long ago. This radon transform actually is used in tomography. It's used in medicine, you know, in medicine and many other things when you do tomography. How you interpret your scattering data. Well, it's also through a radon transform. So this is the point that you get that your double differential rate is proportional to the radon transform. And you can compute, in this case, right, for the eta function, the usual eta function that I defined before, then you can compute exactly what it is. For the SHM with the truncated Maxwellian velocity distribution, the radon transform in the laboratory is this. And then, okay, you have to then impose, of course, this would be if there can be this kind of velocities. So the minimum plus Q dot B labs should be smaller than the escape velocity. Otherwise, you don't have any event. So it should be this one, this function for when this condition is applied in zero otherwise. And here B lab is the velocity of the lab with respect to the galaxy. The lab in this case involves also the rotation, where your lab is, latitude and longitude, and how it moves around Earth. So in this case, you cannot neglect this other component, which is exactly where the lab is located on Earth. So this is, okay. And I think I will stop here because I have a few more that I otherwise maybe a bit too late. I will start from this here. There are a few more things that I have to say, but this is just 3 more. Let me finish. Can I finish a few more minutes so I don't? Okay. So this. All right. So this is it. So there are 2 regimes of interest. When V min is larger than B lab, this argument, the argument of the first exponential, is minimized when Q is in the opposite direction to B lab. That means this is a dipole feature. And this is the dipole feature that you expect. And then at low recoil energies and large wind masses, the maximum of the radon transform happens at an angle, not directly where you would expect it to be, but actually in a ring around that direction. And the ring depends on the mass of the particle. So if you measure actually enough, you have enough data to actually see, not a blob, but actually distinguish, have enough resolution to see what happens where the maximum of the rate is. And the maximum is then in this ring-like feature, then you would be able to have a measurement of the mass of the particle. So this is the ring light feature in this Molvide projection. It is an equal area projection, all right? So you can imagine this is if you have a visualization of a map of the world in this projection, okay? But this is the sky. Okay, once this can be detected, we'll be really in the realm of WIMP astronomy. Now, here it is the following. I mentioned these dark shards. Well, the dark shards, here I hope, the dark shards would generate a blob of some sort outside. So this is the SHM++. So now you know this is the SHM plus the Encelados feature. This is the S++. And this is plus 10% of the dark matter in these shards. 10% can be a lot, right? Maybe smaller, and the effect will be smaller. But if it is 10%, you will see actually a distribution. Of course, you have to have enough data. And there is one more thing I would like to say. There are some weird particle models. In particular, I show you the inelastic exothermic dark matter. And inelastic exothermic dark matter could produce recoils that are in the direction against the direction where you would expect your recoil to come. So you have the dark matter, you would expect your recoils to be pointing in the direction the dark matter comes in. But if you have a weird kinematics, actually the recoils would be in the opposite direction. And that would be a surprise, actually. Instead of coming from this direction in the sky, you will see most of the recoils pointing in the other direction. And that could mean, that would mean, actually, inelastic exothermic dark matter is at play. A very weird scattering. And this is the final thing. Once you are able to see the aberration of WIMPs, namely as you move in daily modulation, as you move in your annual modulation, you would be able to see all these features in the dark matter, then you are going to be in the WIMP astronomy realm at this point. This will be maybe a lot in the future, who knows, but it will be a lot of fun. Okay, I think that this is, thank you for staying. Yes. Well, if you have more than one velocity distribution, speed distribution in the cross section, more than one. I show you for magnetic dipole, right? The cross section has different terms. One is 1 over v squared, the other is constant. I don't know, before. Here. So when you integrate, exactly. Well, the differential cross section may have a trivial 1 over v square, but it may be this is only for SI or SD. Otherwise, it doesn't work, right? You have things that are more complicated. So if you have more than one term, and there are several interactions that are more than one term, more than one term meaning they are usually they are 1 over v squared or constant. Then you have two different integrations, and these functions change differently, and the rate depends on they are multiplied in the rate by coefficients that depend on the nucleus, on the target nucleus. And so, which one is important at what time of the year? And it will depend on the on the particular target, right? Here, for example, we had different targets: germanium, xenon, and so on. These are examples. And you can have various different. This is for heavy mediators or light mediators. And this is the time at which you will have maximum, the maximum of your rate. And you can see actually that they change quite a bit. So if you're measuring an annual modulation in xenon, an annual modulation in fluor, and you see it completely different, it may indicate actually that something like this is at play. So you may not be entirely displeased to find that the actual annual modulations are entirely different. It will mean that you are discovering some property of the cross-section, really. Yeah. Yes?
We talked about the neutrino flow problem, and with the direct, if we have significant directional detections, this neutrino fog is not an issue.
No, but if you are very unluckily that you have very bad luck, it may be an enormous issue. I show you how it will change your how your reach, namely your discovery potential, changes here. If you happen to be here, a spin independent, heavy mediator, and the mass of the dark matter particle is about 7 GeV, you are dead. You can increase your, not kiloton, but you can increase your exposure by a factor of 10,000, which is a lot, and your discovery region will change nothing. At this point, it's very, very difficult. If you have direction, it will be completely different one. That is true. If you have directionality, that changes quite a bit. Because once you have directionality, you go through. Yes, you can perfectly distinguish if something is coming from the sun or is coming from in the direction of Cygnus. I mean, it would be completely different. So once you add a little bit of directional detection, you're in a different realm altogether. But if this is what you have, of course, it depends, because here you will lose, but not that much. And here you lose nothing.
I think maybe we should wrap up and answer questions.
Okay. Perfect, perfect.